a familiar scene. Modern manufacturing. A man, a machine, a method, and sometimes a malfunction. Does this ring a bell? Let's face it, this breakdown could have been avoided and valuable production continued uninterrupted. The fault did not lie with the machine or the twist drill. This drill was damaged because it was improperly repointed. The twist drill will stand more strain in proportion to its size and weight than any other cutting tool. What makes this tool so durable? It was designed that way. Every step in the manufacturing of this twist drill, from the selection of the tool steel to packaging, is very carefully controlled to ensure uniform quality and dependability. We'll see this fascinating manufacturing process in a few minutes. But first, let's look at this twist drill as if it were an assembly of parts. Imagine this as a section of metal rod. Although drills are manufactured in many lengths and sizes, they all possess the same basic features. At this end of the drill is the shank. It's the part which is held in the rotating device. Shanks come in many shapes and types, but the three most common are the straight shank, the straight shank tanged, which is used with a split sleeve, and a taper shank. The marking recess directly ahead of the shank is the neck of the drill. This is the body of the drill. Formed on the body section are spiral grooves or flutes. The angle of these spiral grooves to the axis of the tool is called the helix angle. The junction of the flutes with the point forms the cutting lips. The flutes provide a passage for the removal of chips and at the same time allow coolant to reach the cutting lips. Now, between the adjacent flutes are the lands, which form the peripheral portion of the body. At the leading edge of the land is the margin, and behind the margin is the body clearance. The margin supports the drill in the hole by providing a bearing surface. This helps maintain a straight hole. And the body clearance prevents excessive rubbing and heat generation on the walls of the hole and allows an additional passage for coolant. Drills are also ground with a small amount of back taper to keep them from wedging in the hole. The central portion of the body that joins the land is called the web. This is often referred to as the backbone of the drill. The web may be of either a tapered or parallel construction. The design of the body of the drill will vary according to the type of work performed. And finally, the business end of the twist drill, the cone-shaped surface that does the cutting. We want to go into this point in more detail. It's important. But before we go any further, let's see what goes into making a taper shank twist drill like this one. To start with, high-speed steel for the body section and shank steel for the shank are welded together. And then the high-speed steel end is forged with U-shaped grooves. Then twisted to form rough spiral flutes. The body is turned, and so is the shank. The flutes are milled to form the lands. and the body clearance is milled to leave the margin. Then the drill is hardened. And cleaned. Ground. Surface treated. And finally, the point. And the point is the key to successful drilling. Here is the point. Remember, we mentioned earlier that the twist drill is a hard-working cutting tool. Well, the big reason for this is that while we have a sharp cutting edge, which will shear the material easily out here, cutting edge here is very poor. In fact, it's not a cutting edge at all. It's only a ridge that has to push or squeeze the material out to the side, where the sharper cutting edges can form a chip. This part of the point is called the chisel edge. It's the edge at the end of the web that connects the cutting lips. The cutting lips are the cutting edges extending from the chisel edge to the outside diameter or periphery of the drill. Now, from another angle, the point looks like this. When we look at the side of the drill near the point, the chisel edge is here, the cutting lips here, and this portion of the point is called the lip relief. This is the surface of the drill point which slopes away from the cutting lip. This angle varies with the size of the drill. It should be about 20 degrees for a 1/16 inch diameter drill, and decrease as the drill size increases to about 8 degrees for a 2-inch diameter drill. The sole purpose of this lip relief is to prevent the surface back of the cutting lip from rubbing on the work and impeding penetration. This lip relief is important to the life of the drill. But this can be shown better in an actual operation. This drill has too much lip relief. The life of that point has been shortened considerably. Any point will be ruined if there is too much lip relief and the slope angle is too steep. By the same token, a drill with too little lip relief or a slope angle that is not steep enough will also be ruined. When the lip relief is ground on both cutting lip areas of the drill, an angle is formed between the chisel edge and the cutting lip. This is called the chisel edge angle. This angle usually approximates 120 degrees for drills pointed with lower lip relief angles, and up to 135 degrees for those drills pointed with higher relief angles. Most twist drills have a 118-degree angle point, or a 59-degree angle on the side. A correct point must have both cutting lips ground at the same angle. Not like this, or you'll produce an oversized hole. A while ago we mentioned a balanced point. This means the angles on each cutting lip must not only be the same, but each cutting lip must be of equal length, or again, an oversized hole. Remember, either one of these factors, or a combination, will produce an oversized hole. Now, this brings us to other considerations. Does the material influence the choice of drill, its point angle, its cutting rate? It sure does. The point angle and even the lip relief angle can vary when drilling different materials. This 118-degree point is fine for general purpose materials such as cast iron, steel, brass, bronze, and aluminum. But with the low tensile strength materials such as bakelite, wood, rubber, and plastic, a 90-degree long point is best for drilling. While with the harder materials, such as steel forgings, stainless steel, and die steel, they should really be drilled with a 135 to 140-degree point. These point angles apply to the general purpose drill, the one which you will use most often. There are, of course, drills which were designed to perform a specific duty, special purpose drills. This is a high helix drill. The high helix drill is used with materials such as aluminum and die cast. Because of the consistency of the material, in this case aluminum, the chips must escape faster than with other materials. A high helix in this drill allows the chips to do just that. Now, a low helix drill is best used with low tensile materials, bakelite, wood, and rubber. The harder materials, die steels, forgings, and some stainless, really should be drilled with a heavy-duty drill and a 135 to 140 degree point. These are just a few of the special duty drills. There are many more. But when you use a general purpose drill, know these angles. 8 to 15 degrees lip relief. 120 to 135 degree chisel edge angle. 90 degree, 118 degree, and 135 to 140 degree point angles. Now let's watch some of that heavy-duty drilling which takes place at the chisel edge of the drill. One of the best ways to illustrate what the chisel edge does is to let the chisel edge only do all the drilling. See what happens? The chisel scrapes its way through the material. To make an efficient cutting tool, we very precisely combine the chisel edge with the cutting lips and produce a tool strong enough to push the material away from dead center of the hole out to the cutting lip area, where the chips can then be made. Yes, the twist drill is a hard-working cutting tool, and it will continue to perform quite well unless we disturb the delicate balance of the shearing and thrusting forces that occur at this point. Now that brings us to other basic facts which must be considered every time a drill is used. Among the most important are the speed at which a drill is run and how fast it penetrates the material. Now the speed at which a drill, or for that matter any rotary cutting tool, is run can be expressed in two ways. First, by RPM, revolutions per minute, or simply how many times an object rotates in a minute, and by SFM, or surface feet per minute, or how fast the outside diameter of the tool moves in relation to the work. Here's a demonstration that will help you understand surface feet per minute. Here are end views of two twist drills of different diameters, one about twice as large as the other. They are traveling at the same RPM. However, since this drill is twice as big, it travels twice as far as the smaller drill in one revolution. This distance traveled is called surface feet. Now, to make the small drill travel the same surface distance as the large drill, we must increase its revolutions per minute. Both drills are now traveling at the same surface feet per minute, SFM. SFM is usually used to express the speed at which a given material is machined, because surface feet is common to all diameters, while, as we've demonstrated, the RPM necessary to obtain the given surface speed will vary with the diameter. Each material has a surface feet per minute at which it can best be drilled. Soft materials, such as aluminum and brass, can be run at a speed of 100 surface feet per minute, while the harder materials must be drilled at a much slower speed. Here's a good rule of thumb. The harder the material, the slower the speed. Speed is important, and so is feed. Feed is how deeply the drill penetrates into the material with each revolution. Just keep in mind that every material has a feed and speed rate at which it can be worked most efficiently. If it does become necessary to increase the penetration, it's best to increase the feed rate before increasing the speed rate. Speed and feed charts are available and offer the correct range for drilling. Refer to them. And something else to keep in mind. Many drills are ruined every day by excessive speed, which actually burns off the cutting lip corners. Wherever possible, use a coolant for drilling. A coolant will cool a drill, of course, but more important, well, watch. A coolant should have sufficient lubricity or slipperiness to allow the hot chip to slide easily away from the cutting edge and then carry the heat away with it. While we're here, let's discuss good shop practices, okay? To begin with, To get a good performance from the drill, the operator must give a good performance. Cleanliness is the word. Check that the shank and holder are clean. Dirt will cause the drill to run out. When you seat the drill, use a babbitt hammer. Bad clamping allows the work to spring and can be dangerous. In clamping, make certain that it's rigid. And if bushings are not used, spot the hole before starting the drill into the work. And of course, when bushings are used, be sure they are properly aligned and of the proper size. Then check those all-important feeds and speeds and the type of coolant to be used. You're ready to start. Almost. Here's something that should be almost second nature. Safety. Wear your safety glasses at all times. And think, don't relax. Stay alert. Remove the drill with a drift. A file just wasn't meant to be used for this operation. Handle the drill carefully. Check to see that it hasn't been damaged. Then, after use, store it properly. When it does become necessary to recondition a drill, there are certain things to keep in mind. While there are experienced tool grinders who can repoint a twist drill quite accurately by hand, most of us lack the experience necessary to produce a consistently acceptable drill point by this method. In this case, the drill has been deeply damaged by grinding heat and subsequent quenching in water. Wherever possible, the drill should be repointed by machine. As a drill is used and repointed, it gets shorter, and the web increases in thickness as it approaches the shank. So the web thickness must be reduced for efficient drilling. Usually this is also true of most parallel web drills. Web thinning may be accomplished in several ways. Webs may be thinned on the corner of the grinding wheel, periphery of the grinding wheel, and side and corner of the grinding wheel. Whichever method is used, be sure to remove the same amount of metal from each side to ensure proper cutting action. Wherever possible, this should be done by machine so that the cutting edges are evenly balanced. Care must be taken to avoid excessive thinning of the web, which may cause the drill to chip out or fracture prematurely. Another method of web thinning is to undercut the lips. This is used principally for drilling steel forgings. The point of a crankshaft drill is almost always notched. An offset or split point is good for hand operation. The web is heavy and notching decreases the feed pressure required for drilling. Offset points are used on other styles of drills where the end pressure must be reduced. Offset points also reduce or eliminate drill walking in portable applications. This is a regular drill point with the corners ground off. It's used for drilling cast iron and is commonly referred to as a double angle point. The regular drill point sometimes digs into the work when drilling soft materials. This can be overcome by grinding a flat surface along each cutting edge. This is done on the side of the grinding wheel. There's a point for every application. We've discussed a few of them. Here are the basic drill points, and they each produce their own type of chip. The regular, the notched. the 140 degree, the 90 degree, the double angle, the notched 140 degree, undercut thinning, the flattened cutting edges, the split or crankshaft point, and the shop-thinned regular point. The designs of the body vary according to the work to be performed. Yes, there's a drill for every need. High spiral, low spiral, heavy-duty drills and chip breakers, coolant feeding drills, and screw machine drills. There are special drills, step drills, and subland drills, which cut more than one diameter. Combination drills, which perform more than one operation. Gun drills, twin jet drills, straight flute drills, and half-round drills. There are solid carbide drills, carbide tipped ones, and cobalt drills designed for space-age materials. Drills are used on aircraft and automobiles, bridges and boilers, for tractors and toys. They can be used as one or as many. In fact, just about any way they're needed. That's the story of twist drills, how they're used, and unfortunately sometimes abused. Drills have become a vital cog in our system of mass production. Their value has been proved many times. Twist drills as we know them today didn't just happen. They were a result of a continuous search for better quality in raw material, drill design, and manufacturing methods. The twist drill industry, through aggressive research and development programs, will continue the quest for new and better products.